Hey guys, welcome to this Transformer tutorial. So in this playlist, we're going to go over transformers from all the way to the start to the inputs, right up to the outputs. And we're going to go in depth where I explain the math and I'll give you the code behind it as well. So this series is going to be divided into 4 parts. And in the first part, we're going to talk about the introduction, overview, tokenization, and embeddings. And finally, in part 4, what we're going to do is we're going to tie up all the remaining parts with a real world example. Before we dive into this first part, there are certain prerequisites that you guys have to cover. Let me just quickly go over them. So, number one, you need to know the basics of linear algebra. By basics, I'm talking about matrix multiplications and vectors. The second is you need to have a working understanding of neural networks, how the forward pass happens. The third is obviously the backpropagation part, how gradient descent happens. And finally, you need to know an overview of the RNNs and LSTMs. You don't need to know the exact math and the in-depth reasoning behind each of them, but just an overview on how they work. A high level is good enough for this. So without further ado, let's get started. Let's look at a standard neural network. So a standard neural network, as you know, has certain input neurons that get fed into a hidden layer, and all of these are connected. And then you finally have some more layers, and ultimately they tie up all to the output. Now, if you look at this, you can see a certain constraint. And what the constraint is, there's a fixed number of inputs. Like there's a fixed, it can take in only a fixed shape of an input. And the output is also a fixed shape. There's no variability between the two. So now that does become an issue when it comes to language. So say you want to summarize a text, your text will be huge and then your summarized output will be smaller. And as we know, the text that you enter can be of variable length, and similarly the output should also reflect that. You should get a variable length output. Now this cannot be solved by a standard neural network. So that's why there's something called a sequence to sequence model. So essentially what a sequence to sequence model does is it fixes this problem. So you can take in a variable input, and by variable input I mean variable input size. You can pass it to your model. I'm just going to call it seek to seek model, and you will get an output of variable length. So traditionally these were done using RNNs and LSTMs, but there are certain issues when it comes to this, and let's have a look at this. So consider this input where we have the breadbasket, yada yada yada, till given the inconsistency. This we wanted to summarize it, and we get it after passing it to the sequence to sequence model. We get a summary of the text, which is a decent restaurant, great salmon dessert, inconsistent temperature, pricey for what it is. Now, let's look at the word counts. So the initial input had an 85 word count, and we've summarized it and gotten a word count of 17. So this is exactly what a sequence model does. And as I mentioned earlier, it doesn't have to be an 85 length word count. It can be whatever it is. It can be 120, 130, and similarly we'll get a corresponding output. Now the issue with the traditional models, like for example the ones that use RNN, is that it has a fixed context vector. So what do I mean by that? So this is where the importance of why you should know RNN is there, but I'll give you a brief overview. So an RNN has something known as a context vector that gets updated. Let me draw that out for you. So you've got your input. It gets fed token by token, and in this case, word by word. Don't worry about tokens. I will cover this later. So essentially, you have your input that gets fed one by one into your model, and your model has a context vector. So this context vector gets updated every single time one by one as a new thing happens. As a word comes in, the context vector gets updated. And it's a fixed size context vector. Let me show you this with the help of a diagram that I've made. It'll give you a clearer picture. So if we move on. Yeah, so here's your context vector. We're taking a vector size of 3, hence the 3. And the words that go in one by one are the bread basket. Let's take only that for now. So as the word the gets in, it takes up the full thing. It populates the full context vector. It's gotten 100% of the context. So, but then what happens when we add another one? If we add bread, as we can see, the context vector gets updated. And now the influence of the has reduced a bit. What if we add one more? As we can see, the more we add, the previous context gets diluted. And that's exactly what's called like the memory problem. As the sequences increase, the effect of the previous ones reduce significantly. Now that's an issue. So we need to solve that issue, and that can be done with, guess what, with the help of transformers. But before we do that, there's one more issue we have to talk about, which is, as we mentioned before, the dynamic dimensionality. Hold on. Now you might be thinking, Taran, didn't you just mention the sequence to sequence model can handle this issue? Yes, it can, but not very well. It's done super inefficiently. One, GPU can handle a lot of like parallel computation, especially of matrix multiplications. But the sequence to sequence models, the traditional ones at least, they don't make use of that. It all happens in a sequence, so it takes forever. And especially in the during the back propagation phase, when there's a lot of unrolling that happens, it just becomes a huge computational mess. And that's why transformers and attention, the whole mechanism, is such a beautiful thing. Let me give you an overview of this first. I'm sure a lot of you would have recognized this image. This is the infamous transformer architecture that's given in the Attention is All You Need paper. And throughout this 4-part series, I will be explaining every single thing in detail. But for now, let me just go over this overview. So the model takes in your inputs. Your inputs get converted into something called embeddings, which we will talk about later. Then you're going to need some positional encoding that helps the model figure out the positions, because it gets lost when you convert it into embeddings. And I'll explain how it gets lost as soon as we get to that part. Then we've got your attention head, the main star of the show, that gets fed into a feed forward. So your feed forward is essentially just a neural network. That's all that it is. Then that goes into a normalization again, and this whole thing is called an encoder. And this whole part over here is called a decoder. Now your decoder also has a lot of similar architecture as your encoder, just a few differences. One, you have something called a masked multi-head attention, which I will explain what that is. It's essentially the same thing, but there's just some masking that's required. And again, I'll explain that very soon. And then that gets fed again, as you can see, feed forward. And then ultimately that gets fed into a linear layer, which is essentially just a bunch of neurons. And you get your softmax to get your probabilities to predict the next word. So now let's begin with the inputs. What exactly the inputs are, how it's transformed, that's what we'll be covering in the first part. So let's get right into it. So our input is essentially our corpus. So corpus is just a fancy way of saying a large collection of data. It could be text files, it could be video files, it could be audio, it could be anything. But for this example, we're going to be working with text data, and it has to be large. It has to be gigabytes of data for it to work well. But for now, let's just take a small sentence. The quick brown fox jumps over the lazy dog. Now we need to feed this into our model to train it, right? But there's an issue. Our model just does not understand words. It only understands numbers. It knows how to deal only with that. So we need a method to convert this sentence into an array of integers or any other sort of numerical representation. And this whole process is what's called tokenization. So tokenization is essentially nothing but just mapping your tokens into its corresponding integer. So for now, let us consider each word as a separate token. So how would that look? If you look down, yeah, we split it into words, and we treat each of these words as a token. Now, later on, I will explain the byte pair encoding algorithm, which is the way modern LLMs handle the conversion of your data into tokens. But for now, for understanding, let's just stick with this. So let's move on. So we've got our unique tokens. We consider only unique tokens. So, and here it goes both ways, not just one. So the word the gets mapped to 0, the word quick gets mapped to 1. And if we look at it, here is what we get. We take this full sentence and we've successfully converted it into a list of integers. And this is what the model can understand. It can understand numbers. So we've done tokenization essentially. And mind you, here we've taken words as tokens, but it could be like part characters, like th could be a token, space qui could be a token. It needn't be a word. A token is just a collection of strings. So that just depends entirely on the algorithm used, and it's up to you on what to use. But generally speaking, people do use BPE, at least modern LLMs do that. So let me just walk you through a code example of how this tokenization process would work. Now we'll look at the code to do the word level tokenization. So I've written some functions here. I've not written the contents inside the function yet. I want you guys to pause the video, try to fill it out by yourself, and then come back to it to look at the answer. So the get vocab list function, what it does is it essentially gives you the list of all unique words. So what we need from this function is a list of all unique words. So let me implement that really quick. Again, I want you to pause and fill it out yourselves. So we need a list of unique words. So in Python, you can create a dictionary using to get all unique words. And from keys gives you only the key values. So we want to make the strings lowercase in this case because for now we don't want to worry about capitalization. But when we get into the BPE algorithm, all of this will get sorted by its own. So you want to lowercase the string and then split it. So this is essentially your get vocab list function. You get your words. Now your next function is going to be get your word to token index mapper. So what that means is it's this part. Let me quickly switch over my screen into OneNote. Yeah, there we go. So we want this part, the from the going to 0, quick going to 1. So this is what this mapper does. So let's look back at the code. Okay, let's write it out. So what do we need? We need our mapper. So our mapper for now is going to be an empty dictionary, and we want to return your mapper. Now, so for each element in your vocabulary list, what do we need to do? Well, we need to check if the element, if it's not in the mapper, we simply add it. Mapper of element is equal to, and here we're going to need an index to keep track. So let's keep an index of 0. Let's do that, and let's do index plus equal to 1. Now that we've got that written out, we're going to need the inverse method. We're going to need to get the index, and then you get back the corresponding word. So what this method does, again, we've got a mapper, but this time it'll be the inverse. So we want to return the mapper, and this takes in your initial token mapper. So what do you want? So for key and the values in token mapper dot items, essentially what we want to do is the same thing. So a mapper, but here the value will be equal to the key, and then we return it. Then we're going to need an encode method. So the encode method takes in a list of tokens, your mapper, and your output, you get back the list of your encoded token. So we want your encoded list. Let's return that. So what do you want? So for element in your input token input, you want to do encoded list dot append and your token mapper of your element. Yeah, that's essentially it. And your decode is the same thing but inverted. Here I can write it out in reverse. So we could put token for uh, element in encoded tokens, and it's or let's yeah, and we're gonna need the index mapper of this, of not your token but your element naming conventions. Now we're gonna test and see if this works. So what we're gonna do is we're gonna get our token mapper. Token underscore mapper is equal to, what's the function name? Oh, we're gonna need the vocab list first, sorry. So your vocabulary list is gonna be get vocab list of my test string. Then the token mapper is gonna be the get index to token mapper of, we're gonna need to pass in our not index, sorry, get word token index mapper that will take in our vocab list. Then we need our index mapper, which is essentially the inverse of this. And we're going to print it now to see if everything is working in order. So let's take an f string. So my vocab list is going to be this. And we're going to print the vocab list. Then we're going to have the token mapper. And finally, the index mapper. Index mapper. Okay, let's run it and see if everything is in order. Let's run it. And as we can see, we've gotten it. Let me zoom in a bit. Yeah, we've got our vocab list. The quick brown fox jumps over lazy dog. Remember, the is not unique, so we need only one. And oops, looks like I have made a mistake here. Oh, there we go. That was my mistake. Uh, let's fix that. Yeah, there we go. We've got our corrected output now. Let me just clear my screen. And let's run it again. There we go. There we have it. We got our token mapper with the 0. All of that works. Perfect. Now let's see if our encode and decode methods work. So we're gonna say print the encoded version. That will be encode. We need to pass in our list, which is essentially going to be our test string dot lower. Remember, we're dealing only with lowercase for now. We're gonna split that and the token mapper. Let me just fix this also. Print. And let's see if our decoded output will be the same. So let's write the code for the decoded. And we're going to just do this. And our index mapper. Let's run it and see if that works. And wait, let me pipe the output into a file, output.txt, and there we go. We've got it. We got our encoded string, and when we decode it, we get back the same one. Now that we're finished up with the word-level tokenizer, let's get into byte pair encoding. So byte pair encoding is essentially a tokenizing algorithm. So you have to train it first. I'll explain what the training process involves. And then, yeah, you have your same encode and decode. So in your training process, there'll be multiple iterations. You can stop whenever you decide. You can stop at the second, you can stop at the third iteration, you can stop at the 10th, you can stop at whatever iteration you want to. So let me explain what happens in a single iteration. So first, what we do is let's take this sentence. Betty bought some butter, but the butter was bitter. And before that, in the traditional BPE algorithm, we work on strings directly, but for LLMs, we convert them into bytes using UTF-8 encoding and then use the BPE algorithm. But it's the same process. So BPE is essentially a greedy algorithm. And for those of you in a CS background, if you remember Huffman encoding, where you take the least common pairs and you merge them, this is essentially a similar version, but we take the inverse. We take the most frequently occurring pair. Let's analyze this sentence. Betty bought some butter, but the butter was bitter. So, what are the possible pairs of characters? We've got BE, ET, DT, DY, Y space, space B, and so on. So, out of all these characters, all these possible pairs, we find the most frequently occurring one. So, it looks like space B seems to be the most frequent, which is 1, 2, 3, 4, and 5. And then TT also looks pretty frequently. 1, 2, 3, and 4. And 4. So now we take the one that's the most frequent, which is underscore B, and we substitute it with a new character. So let's substitute underscore B with, let's say, a diamond shape. So what happens now? Now your new sentence will look like Betty, and instead of space B, you've got your diamond. You got dot 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 dot, and your sum. And instead of space B again for butter, you got your diamond. And we continue this process. So this is your first iteration. You got the most frequently occurring pair, you merged it. Now second iteration, again, you find the most commonly occurring pairs. In this case, TT itself is the most commonly occurring one. So we substitute TT. So let's, instead of TT, let's substitute it with a circle. Let's take a circle for now. So you got Betty, a circle, Y, diamond, and you continue and you do this. So you do this for how many ever merges you decide. It's up to you. There's no fixed limit. So after that, what happens is we then proceed with the same encoding procedure we did before, where we take the index and we convert it. We take it and convert it. Now let me explain it to you on the byte level. So I'm going to talk about UTF-8 for a bit. I urge you to go read about it on yourself, but I'll just give you a brief overview so that you have an understanding. So according to the UTF-8, it has a maximum size of 4 bytes and a minimum size of 1 byte. Typically, all ASCII characters occupy only one byte. So that's 8 bits. Then your emojis take up all 4 bits, actually. 4 bytes. And there's certain characters and in languages, like the ones with accents like this, they take up more than 1 byte. They take up generally 2 bytes, and Japanese characters or Chinese characters take up 3 bytes. So we're going to apply the same algorithm shown here, but using this UTF-8 encoding. And I've got an example over here. So the same sentence, Betty bought some butter, but the butter was bitter. And I've added a butter emoji has a length of 52, including spaces and everything. But when we convert it to bytes, we get 55. Now, why does that length difference comes? Well, that length difference comes again because I showed you that you've got 4 bytes. It takes up 4 instead of 1. And the regular ASCII characters like B and its equivalent in UTF-8 is 66, and E is 101, and space is 32. So now we perform the exact same algorithm with the merges to get our BPE that's used by LLMs. So let's look at the code for that. Before we move on to the code, actually, there's one more point that I want to address. So when it comes to UTF-8, so we know that 1 byte is 8 bits, right? So if there are 8 bits, that means there are 2 to the power of 8 possibilities, which is 256. So that means, according to the UTF scheme, the unique characters are only between 0 to 255. So every subsequent merge will add a +1. So if there are 5 merges, your vocab size would be 256 plus your number of merges. So keep that in mind. So as we increase the number of merges, your vocab size increases. But the good thing about UTF-8 is it's got a 256 unique characters, and if we stick to a lower number of merges, we will not have that many characters, unique characters, that is, unique tokens, I should say. So yeah, just wanted to clear that out. So any new merge tokens, we will be starting from the index of 256. So if underscore B would be 256 and like DD would be 257. So yeah, now let's get into the code. Let's take a look at the boilerplate code that I've written. So I'm going to explain what each method does, and I urge you to try and write the code by yourself, and you can come back and refer to the answer. So your init method, what are you going to need to initialize? So one, you're going to need to initialize the number of merges you required. Another thing you need to do is keep track of the merges. So which 2 token IDs get merged into and what's their new corresponding token. And third, you need the mapper, which has the unique the token, and you're going to give it its corresponding unique index. So let's start writing the code. So again, you're going to need your number of merges. So that's essentially just this. You're going to need to keep track of your merges. So this is going to be a dictionary, like a map essentially. So this will have your token ID, your second token ID, again, because it's pairs, and your value is going to be your merge token ID. Then after that, what else do you need to keep track of? You're going to need the vocabulary, of course. So that is essentially just I need bytes of I. Sorry about that. Bytes of I for I in range 256. So there's your initialization. And you don't need a return for your init method. That's automatically called. Now your training. Now your training also returns null. So let's start off with this. So your sequence. So how's your training? You take your sequence. You need a sequence of your bytes. You got your input as your text string. Then you're going to need to have your next ID, which will be 256 in our case. Then we're going to have to run a for loop throughout for the total number of merges. So let's start with that. So you got your sequence, which will be nothing but your text is actually going to be bytes of your text dot, and we're going to encode it in UTF-8. And this has to be in strings. And oh wait, I'm sorry, I don't think it's not bytes, sorry. You're going to need your list. There we go. Your next ID will be 256, your new character, your new merge. Then we're going to need to run it for your total range, which is in range yourself. We're going to call the number of merges, and then we're going to start. So first, we're going to need to keep track of your counts. Now let's create the pair sequence. pair sequences. So it's going to be, so we're going to run it in a sliding window. So we're going to run it from the range. It's going to be length of your sequence, -1. So why -1? Because you're gonna see when we take the pairs, we're gonna take I and I plus 1. But I plus 1 can throw an out of bounds error, so that's why we have to ensure that we don't do that and go out of it. So if you got your pair is nothing but, it's gonna be your sequence of I and the next character of I plus 1. So after you got your pair, we're going to need its counts. So what we're going to do is first going to check if it's in counts. So rather than writing an if else statement, I'm going to use Python's get function to make it easier, and I'll explain what it does. So counts.get pair and 0 and +1. So what this does is it's going to get your counts. If the pair is not there, it's going to return. This will give you 0. And if it's there, like let's say you got a frequency of 2, this method will simply just get the 2 and it'll increment it by 1. So rather than writing an if else, this is just a cleaner way of writing it. Then we're going to have to add some edge cases. So if not counts, then we need to break out of it. And another thing, what happens when all the frequencies are just 1? Then we can no longer possibly merge. So we need to break out of that. So if counts, or before that rather, we're going to need our best pair. So our best pair will be, we need to take the max element of counts, and we're going to do it on the key value, which is just counts.get. Oh, why is this throwing an error? Oh yeah, I have type checking. I'm just going to ignore this for now. Don't worry about that. That's just Python making sure that there's no type breakage that happens. But we can ignore that for now. And then now, as I mentioned, if your counts of your best pair is less than 2, so essentially if it's just 1 or 0, I mean, it can't be 0, we're going to break out of it because our merging is done at that point. Now we have to record the merge. So we're going to add it. So in our self.merges of your best pair, that's your key, is going to be your next ID. And your self.vocab of your next ID will be nothing but your self.vocab of your best pair of 0. And it's going to be the same thing, but of 1. Then what are we going to do now? Let's apply these merges. So we're going to need a new sequence. Let's initialize it to an empty list. We're going to need an index tracker. So while I is less than, we need to run through the sequence length. Now we need to check if the pair is there. So if I is less than, first we need to check the edge cases. So I has to be less than length of sequence -1. And if your sequence of I, or should be a tuple, the sequence of I, and your pair rather, sequence of I plus 1, if this is equal to your best pair, then to our new sequence, we simply append the next ID. And then we got to increment I, but not by 1, by 2. If not, else what do? We just append the input as it is. So new sequence dot append just sequence of I. And here we just increment it by 1. Then our sequence will now be equal to the new sequence for this case, and your next ID will get incremented by 1. So this is the training process. And again, we return none in this case. So now let's move on to the encoding part. How is it going to get encoded? Now the encode method will have essentially the same, it's pretty much the same code as this over here. But the only difference is we'll be iterating through the list. So it'll be for pair in merged ID. Oh wait, first we're gonna need our sequence. So sequence is equal to list of your text dot encode and same UTF-8 of your text. Then for in your self dot merges dot items, we have to iterate over this, and it's essentially the same code. And here instead of next ID, it's going to be merged, and instead of best pair, it's just going to be pair. And we just return the new sequence. We're going to add this also. Your sequence is equal to new sequence. Yeah, and we will just return our sequence. And your decode, well, I can write a short form of this. So essentially what we have to do is we're going to combine the string. We're just going to, it's going to be the reverse map. So self.vocab of t and for t in token IDs. And then we're going to dot decode it into a UTF-8. So yeah, this is essentially the code that's done. So I've written some code over here at the bottom for the example usage to just check if everything is in order. So we're going to run it. Let me clear this. Let's run this. Oh, let's actually pipe this into our output.txt. But first, let's actually clear this. Let's ensure that this is cleared, just to double check whether it's working properly. And output.txt. Yeah, as we can see, we got our original, which is 55 bytes. Then when we've encoded it, we've got only 37 tokens because of the merges. And when we decoded, we got the same. And the round trip is essentially just checking if whatever we encoded, if we decoded, whether we get back the same. Our vocabulary size, since we took 5 merges, is 261. And here are the merges that have occurred. So there we go. Now that we're done with tokenization, we need to get into the further parts of how to transform the input. Now we need something called an embedding. An embedding is essentially just a vector of dimension whatever you desire. Let's take 384. So why do we need embeddings? We've got it in integer form. Why not just give it? Well, one thing is, in higher dimensional vector space, the learning happens in that where the alignment and all the attention, that just simply cannot happen in lower dimensions. It's not enough to represent it. That's why we need to convert it into embeddings. So now that we see here, right now I've just taken the word-level tokenizer. I'm not taking the BPE. Again, this is just for explanation, but I'll show you in code how to use the BPE inputs. So now we got this 0, 1, 2, 3, 4, 0, 6, 7. So now 0 should be associated with a vector of numbers, like let's say 38.1 and its size should be 384. Similarly, 1 should also be represented by a vector. 2 should also be represented by a vector, and we keep going on. So each item in the vocab list, in the index, essentially your vocab list only, you require the corresponding vector. So this is what essentially embedding is. So embedding is a way of representing your word/token in terms of vectors. And this right here is what we call the embedding table. So we got a token. Right now I've just written but it's actually the index that gets mapped. So 0 will get mapped to this vector. And you've got your embedding table. So your embedding table, if you look at this, if you were to take its shape, what would it be? What would its shape be? So we know that this, again, if we take this as a 384 vector, this is, and we've got 8 unique rows. So the shape is essentially just 8 by 384. That is your embedding table. This is what your model learns and modifies. So the embeddings get modified throughout the training process during the backprop specifically. And this is how the model learns. It aligns the different vectors. It gets the attention, which I'll explain in the next video. But for now, just know that the embedding table is essentially just a lookup table. So whatever your corresponding ID is, token ID, you get its corresponding vector. And the shape is 8 by 384. So this is how the embedding parts work. Now, before we get into the input embeddings, let's understand what context length is. So context length is essentially the length of tokens your model can take in at once. So if you have a 256 token model, it can take in at one time, I'm saying it can take in 256 tokens. And if it's a 512 model, again, we got 512 models. So what happens if your text is more than these tokens? What if it's 10,000 tokens? What are you going to do? So for that, I've got an example for you. We got a paragraph and we want a maximum length of, the model can take a maximum of 5 tokens. So what do? So we have to chunk out our data. So one, we can chunk it without overlap and with overlap. So by without overlap, I mean, let's look at the sentence. So if we take this, look at the chunking, the quick brown fox as one part, and then no to the woodland locals, another part. But if we take with overlap, if you look at this, the quick brown fox, no to. So generally, we depending on the size of your data, you would go for either. If you have a smaller size data, you would prefer one with overlap than without overlap. But generally speaking, if you have a large enough data set, without overlaps works just as well. So now let's get into the input embeddings. Now your input embeddings, we have to take into consideration the context length. So if we take the context length as 256, that means, as we can see here, we've got 256 tokens. And again, I'm taking an input dimension of 384. What do? We take these tokens, we find the corresponding vector from the embedding table, and we get back our array. So if we take 0, its corresponding vector is 12.8, 3.98. We can see here 1. We can see we got it back. And then the next sequence is 7. So what is the 7's vector? Here we got it, and it keeps going. And the shape of this, if you could guess it, you're plugging it into the embedding table. So you got 256, and for each of them, you're getting back the corresponding vector. So your input shape or your input embeddings is 256 by 384. This is its shape. Now let me show you the code of this. All right, so I've written out the code for this one because I'm just going to show you the naive approach if it was native. But since we have PyTorch, we don't really need all of this. But I'm just going to show you how much PyTorch can simplify this entire process. So we're going to define a few terms. We got your vocabulary size, which is 256, and your embedding dimensions as 4, and your context length is 6. So we're going to create the embedding table. So this code creates it. Here we randomly assign a vector of dimension 4. Then we print it. Then this is the input tokens. And then, yeah, during the forward pass, we're going to use it as a lookup table. This is essentially what it's doing. And then we append it and we get our corresponding output. Now I'm going to run this. And again, I will pipe it out into output.txt for it to be clear. Now, if you look at output, yeah, we got our embedding table shape, 256 rows, 4 columns. Our input shape is 6, which is just the token IDs. And the resulting, here it is. We get the corresponding vector, and our output shape is 6 by 4. So this is our input embedding. Now let me just show you the brilliancy of PyTorch, like how much it simplifies this process. All right, so we're going to import torch first. Then we're going to import torch dot nn as nn, and let's start. We're going to copy paste some of the code. We're going to be needing this, and we will need our input tokens too. So we're going to need our embedding layer, which is going to be our embedding table. It's technically a layer, but let's name it as table for simplicity. It's going to be nn.embedding. Now the shape of the embedding is going to be your vocab size and your embedding time. Then what you're going to do is now that we got our layer, now we got our input tokens. Let's show this. Now we're going to get our input embeddings. So our input embeddings is going to be nothing but our embedding table, and we're going to pass it essentially a lookup input tokens. And finally, I'm going to copy paste some print statements so that I don't have to type it out manually. So yeah, we've got this, the dot shape. Oh yeah, it's going to show me an error because again, let me just type ignore this. And let's run this output. Oh, looks like I have made a mistake. Oh, let me just quickly check what I have done wrong. Let's read that error again. Oh, yeah, I know what mistake I have made. Sorry about that. It has to be a tensor class. So it's going to be dodge.tensor. There we go. Now it should run. Let's see. Yep, it ran. And you know what? Just to ensure that there's no funny business going, I'm going to subtract this. And I will show you exactly what we get. If we look back at our output, there we go. Our input shape was 6, our tensor. Got an output shade of 6 by 4. And here we've gotten our input embeddings. So this is how input embeddings work. Now, if you look at this, I'm going to switch over to OneNote real quickly. Let me make sure you guys can see that. Yep. So our model took in the entire part. It took in 256. It's taking this whole input embedding as one. It's taking the full thing. Now that poses an issue. If it takes it as a whole, we've lost the positional values of each of the token. So that's why we need something called positional embeddings. So let's move on to positional embeddings. So according to the model, let's look at this. So according to our model, the quick brown fox jumps over the lazy dogs is the true sentence. But for the model, all of these are equivalent. Dog lazy, the over jumps, the dog jumps quick brown, the lazy jumps over. All of that is equivalent as we discussed because it takes the whole text at once, unlike our sequence to sequence, which took it one at a time. So that's why we need the positional embeddings. So the positional embeddings will have the same shape as our input, as our embedding dimension. So since if we had a 256 by 384, this should also be 256 by 384. So this is the formula that we use to calculate it in the paper. Attention is all you need. Oh, you know what? Actually, I wasn't going to do this, but let me give you guys a bonus. Let me give you an intuitive reasoning as to why this particular formulas were chosen. Let me just create a new page. Okay. Okay, let's look at our positions. So we got. Okay, let's take some binary representation. So let's say position 0, and let's take 3 bits. So 0 in binary will be represented as 000. 1 in binary will be represented as 001. 2 in binary will be represented as 010. 3 is 011, and 4 is just 100. Now, if you look at this, it's just flips between certain bits. Now, the issue with just using binary is it's discrete. By discrete, I mean it happens like there are only certain numerical values. It's not smooth, it's not continuous. So like example, if you take small, medium, large, those are examples of discrete. But we want something continuous and differentiable because again, during backpropagation, we just love functions that are smooth so that we can differentiate them easily. And discrete functions are notoriously difficult because they don't have any continuity. They're discontinuous, so you can't really differentiate them. So in order to do that, that's why we take the sine waves. So the sinusoidal and the cos waves show the same bit flipping thing, but it's in a nice continuous manner. So that's why they've gone and chosen this. This is the intuitive reasoning, not the exact derivation behind why, but this will give you a good understanding. So we got our positional embeddings. Pos of 2i is equal to sine pos over 10,000 to the power I by d model. So d model is just your embedding dimension. So position is the position of the word in sequence. Mind you, all of this is zero indexing. We don't start with one. I is the index mapping to that dimension. And for all odd dimensions, we take the cos, and for all even dimensions, we take the sine part. So let me understand this. Let's make this more clear. Let me plug in some values so it's easy to understand. So as we've established here, we want our embedding dimensions to be 4 dimensions. So we need a vector of length 4. So vector of length 4 means, yeah, 4 dimensions. So your dim 0, 0 is even. So the dimension is even. So we take the sine. So sine, your position 0. So 0 over 10,000 into 2 star 0 by 4. And your cos, your dim 1 is an odd dimension. Again, we're using 0 indexing. So again, it's 0 over 10,000 into 2 star 0. So here, note that it's 0 and not 1, because if you look at the sequences, let me just show you. Let's take this. So if you look at even numbers, 0, 2, 4, 6, let's say 1, 3, 5. If you look at their actual indexes, this is in the 0th index, this is in the 0th index, first index, this is also first index. So we take its corresponding occurrences according to this. So dim 1 will actually be 0 because as we've established here. So, and then now if we move on, 2 is technically the first one in this. So that's why it's 2 star 1. And cos again, it's 2 star 1. And then here we get our final values. And mind you, all of this is in radians. It's not sine of 0 degrees, it's sine of 0 radians. Keep that in mind. So similarly, for position 1, we calculate it. Again, same formula, but here instead the position is 1, so it's all 1. And the rest of the formula remains identical. So your final vector, so your position vector for 1, according to this, is just going to be 0, 1, 0, 1. And this, your position 1 vector, will just be 0.841, 0.540, 0.010, and 0.999. And now finally, across all of this, what do? So we get, if we take 256 positions, the 256 sequence length tokens, and let's say 384 instead, because we use that for our input embedding. So this is our input embedding. Now, as I mentioned, then we take our position embeddings, which we just got right now, which will also be the same shape. And we simply just sum these two up. And that is what gets fed into your first attention head, this combined input. So that's it for this. Now let's look at the code and then we can wrap this video up. We're finally reaching the end of the video. Now let's just look into the code. So I've written the PE function. So this returns the position embedding for the corresponding position. So if you give it position 1, it'll return the corresponding position vector. So let's just start. So we need our position embeddings. So we're going to return our positional embeddings. So first we're going to initialize it. So the shape of this would be your D model. Now we need to iterate it for odd ranges. So for I in range, then we will have to do d model divided by 2. Our denominator is, let's look at the formula again real quick. Let me open up OneNote. Yeah, as we can see, sine, our denominator is 10,000 to the power I. Got it. So let's quickly head back to this. So that's math.pow 1e4. This is just a way of writing 10,000 into 2 star I divided by your d model. That is your denominator. Now your PE of 2i, 2 star I, will be math.sine, your position divided by your denominator. And your PE of 2 star I plus 1 will be the cos version, cos of pos over denom. And we simply just return PE. But here we're taking only a 4-dimension model, and we're going to go up to 10 positions. So how do we get all PEs? That's very simple. This function is to get all the positional embeddings for that particular, up to that particular max position. It's just simply torch.stack. So torch.stack just literally just stacks up all the position embeddings. So we don't have to worry about any of that. So it's torch.stack. Then we're going to call in our method P for our pos for position in range our max positions. It appears to be throwing an error. Yeah, this is, again, we can just type, ignore this for now. This is just my linter crying. We don't have to worry about that. Now, I've written a helper function for printing. I'm just going to copy that. I'm going to paste this, and I'm going to call it, and let's see if it works out properly. So let's run this, run the file. Oh, it seems to be working properly. Again, let's pipe it, put txt. And look at that, we've gotten it. And we can verify this with our OneNote, which is exactly what we got. We got 0101, 0.84, 0.54, 0.01, 0.999. And there we go. That's for position 1. And we moved up to 10. So again, since we start 0 indexing, so it's up to 9. And these are the position vectors that we get for it. I hope you guys enjoyed this video, and I hope this was informative. It might be longer than what I intended to, but I wanted to cover as many concepts as I could to give you, and in depth, to give you a clear understanding. So with this, we can move on to, we can just switch this over. Let me just switch my screen. Give me a second. Yeah, and with that, this concludes part 1. We are done with part 1. Let's mark it in orange. So next up, we will be starting part 2.